Greetings and welcome, Internet friends. Today we are continuing our look at Intercept's form for quadratics and kind of extending some of those ideas. So this is from 8.5 in your Big Ideas Algebra 1 text, although perhaps you're doing this in Algebra 2. It happens kind of equal frequency for both of those things. And so we've learned that a zero of a function is an x value for which y equals 0, when the function equals 0. You can use the intercept form of a function to find the zeros of a function. All right, and so functions have zeros. So for instance, a function may output 0 when it has a given input. And those are synonymous in many ways with the x-intercepts that a graph has, right? If I graph the function where it crosses the x-axis, that's where the y value is 0, where the y value is 0. And so that is going to be the same thing. So even I will not perfectly use these words in full accuracy. They're nearly identical because they are talking about the same set of numbers for a particular function and its graph. It's talking about where it crosses the x-axis, right? So let's find the zeros of a function. So here's example 3, and this is going to occur whenever the function f of x is 0. So I'm not plugging in 0 for x, I'm plugging in 0 for f of x. So f of x equals 0 will give me the zeros of a function, and 0 is equal to then x minus 1 times x plus 2. And this should, back into our solving by, factoring days, remind us of the zero product property. Perhaps you recall? Property. Boom. And this is the idea, is that if 2 things or 3 things or 7 things multiply to be 0, which is kind of what these 2 things multiply, equals 0, right? Therefore, at least one of them is 0. And so either x minus 1 equals 0 or x plus 2 equals 0. And so solve kind of using your inverse operations algebra 1 solving method. There's 1 and subtract 2 and I get x equals negative 2. So notice, first of all, that the zeros of a function are not necessarily equal to 0 themselves. This is when, if I plugged this into the function, I would get a 0 as the output, although they could technically be the zeros. And so let's graph this. Tell you what, even though this isn't asking for us to do that, x minus 1, x plus 2, let's graph this just to see. So if I had f of x equals x minus 1 times x plus 2, notice, what am I talking about? The x-intercepts. Boom, right there. Negative 2 and 1 are where these 2 things cross the x-axis, which is when the y value, notice the y value for both of those are 0, and therefore the output of the function is 0 at those times. So that's kind of the whole idea. So if I was using an equation in order to find the zeros of a function, I'm plugging in 0 for f of x and solving. Oh dear, let's see. Now here's a relationship between factors and zeros. If I have a factor of the form x minus n, then n will be a 0. Notice the oppositeness going on here, right? And some of you, I know back when we were solving by factoring, had already noticed this relationship, that there's a way to, once I factor something, I kind of just opposite it and it makes sense. And so if I want to find the zeros of these 2 functions, I'm going to plug in 0 for f of x, and then I'm going to factor these and try to figure it out from there. So if I'm factoring this, notice I'm tempted to jump right into AC method here, except my first move should always be to check for the greatest common factor. And so I'll steal a negative 2 from every term, leaving me x squared plus 5x, because negative 2 times 5 is negative 10. And negative 2 times 6 would give me the negative 12, so that's a positive 6. Remember, this is still an equation, so I've got to still have that equal sign there. I can't just forget to write it. And now this yellow part is further factorable. Its leading coefficient is 1, so I don't have to do AC method, although I'm perfectly allowed to. I'm going to find the factors of 6 and which of those add to be 5. 2 and 3. Boom. And so I'm going to have the following. Negative 2 way on the outside times, and I'll have two sets of factors here. So x with a 2, x with a 3. They multiply to be positive, so their signs are the same, and they add to be positive. So plus plus, I think, is the only combination. Set this equal to 0. And now I can use the zero product property. Is negative 2 ever going to equal 0? Nah, not never, not ever. Sorry. So negative 2 equals 0. That's just not true. X plus 2 could equal 0, and x plus 3 could equal 0. And actually, you don't even have to do this. We could have just used our new little property that as long as the number in front of the x is a regular 1, right? If this said like 3x plus 2, I can't just opposite the constant. But in this case, I can just opposite these things, and I would have gotten x equals negative 2 and x equals negative 3. And so those are the zeros of this function. And tell you what, we might as well continue to confirm this for you, that you increase in your belief of this fact. So what's that? Negative 2x squared minus 10x minus 12. Let me jump right in here. Negative 2x squared minus 10x minus 12. Here we go. And so behold, I get zeros at negative 3 and negative 2. Would you look at that? And so once again, these do have 0 as the output, so the y coordinates, and that's why zeros and x-intercepts are talking about the same thing. All right, check this out. Now, this is not fully factored, this problem here. I'll tell you what, let's actually plug in 0 for the output. And so I'll have x minus 1. And, fine, I'm out of space. I'll write it down. X squared minus 16. This part here is further factorable. There's no GCF. Can't steal yoink yoink from both terms. But it only has 2 terms, which has me thinking about the difference of squares pattern. And hey, we haven't written that down in a while. So why not write that down? Write that down. Nope, Mr. Waddy, you're doing it wrong. It's a good thing. Here we go. A plus b times a minus b. Boom. And so here's the difference of squares pattern. So a would equal x because x squared is x, and b would have been 4 because 4 squared is 16. And so now I'm going to have an x minus 1 still hanging out from right there. And then this a plus b, a minus b, so I'll have an x plus 4, x minus 4, still equal to 0, still equal to 0. And now, actually, wait, let's avoid the full 0 product property. I think I can just write x equals, the opposite of that is 1, the opposite of that is a negative 4, and the opposite of that is positive 4. And so this, wait a minute, has 3 zeros. That means it has 3 x-intercepts. Now think for a minute. How could a parabola have 3 x-intercepts? Visually, it could hit at 1 point. It could hit at 2 points. It could hit at no points, right, if it just never crosses the x-axis. There's something unusual going on here. This is not a parabola. This is not a quadratic. In fact, if I was to FOIL all of this out, I would end up with a 3rd degree as the highest term. So this is a cubic function. And tell you what, let's see what that looks like. So x minus 1, x squared minus 16. So in parentheses, oh dear, x minus 1, oh, come on. And x squared, what? What? Look at this. This is like a weird looking shape. Let me squish this in one direction. So this is a cubic function, raised to the third degree if I was to FOIL it out. But notice a 1, a 2, a 3. I do in fact have 3 zeros here, and I believe they correspond to the very ones that we just got, right? I'll have to delete that later, but notice here's the -4, here's the 1, and there's the 4. Bop, bop, bop. 3 in a row. And so even though I wouldn't have known how to graph a cubic function yet, I would have been able to from this particular equation by factoring it. I could have found every time it crossed the x-axis. Now, just a foreshadowing, by the way, this is not a vertex. This does not have an axis of symmetry right there. Weird behaviors, also not a vertex. Y-intercept you guys could have figured out if you multiplied it all out, but yeah. So anyways, so there we go. Let's take a look at this one. So how could I graph a quadratic using zeros? Well, I guess we could put it in intercept form, really, which means essentially I'm factoring this, right? That's essentially all I'm doing. And so h of x equals, there's no leading coefficient, or it's an invisible 1. All right. So I don't have to AC method, so I'm just going to find the factors of c that subtract to b. And 1 and 3 are them. And so I'll have an x with a 1, an x with a 3, and there's signs. They multiply to be negative, so they must have different signs, and they add to be a -2, and so the larger number, the 3, must have been my negative, and the 1 must have been the positive. And so therefore the zeros are going to be -1 and +3, because remember that the little opposite trick, opposites, opposite, right? OPP is what we end up having here. So let's graph those, tell you what. So here's -1, here's +3, and now what else can I find here? Well, I can find, well, this was originally in standard form, so the y-intercept would have been -3 right there. I also have a couple tricks up my sleeve. I know that a was equal to 1, so this is a regular parabola shape. It isn't stretched nor smooshed, and I also know, so that means it's going to have slopes that are 1/1, 3/1, and 5/1 for quote-unquote slopes. That still might not perfectly help me figure everything out. But remember that this is going to be mirrored over the axis of symmetry. So my h value, or v sub x I've called it sometimes, the x coordinate of the vertex, has got to be halfway between these two intercepts. And actually, you guys, we did do that the other day, didn't we? Using zeros. So h is going to equal -1 plus 3 divided by 2, which is 2/2, which is 1. And so there's my h. And I could actually find the value of k by plugging this in, but I suspect, it's going to land right there. And does anyone know why I'm so suspicious of that? Well, I know that since it's a regularly shaped parabola, it had to go up 1 over 1 and up 3 over 1. And that's the only way it was going to kind of meet that within that space. And actually, tell you what, let's keep going. And then up 5 over 1. And there's no room for 7. I don't need an ellipse right now, but I do need to draw my parabola. Ugh, gross. And this is a sad-looking parabola, but it's okay. Don't let it ruin your day. Draw some arrows at the end of that, and that's pretty good. What's the other way I could have found k? Well, I heard you guys asking that in your head. So k, remember, I could have found by plugging h into the function. That's actually annoying that the function was called h and this input is h. That's quite annoying. So I would have plugged in 1 for both of the x's. So I would have had h plus 1 times h minus 3. Tell you what, I'll do it in blue, Ba-da-ba. And so I'd get equals 2 times negative 2 equals negative 4. Tell you what, here we go. So k equals negative 4. So I can see my vertex, boom, was at 1 comma negative 4. So a bunch of ways that you could have gathered that information and you would have been good to go. All right, well, thanks for watching, Internet friends. I'm out. Have a good day.